Thank you.
Our next speaker, Hugo Paquet from Oxford, is contributing a talk on almost surely terminating probabilistic programs, or stating that almost surely terminating probabilistic programs are differentiable almost everywhere.
Yeah, thank you. I'm just sharing my screen. Sorry, 1 second. Okay, hopefully you can see this.
Looks great.
Yeah. Great, thank you. Sorry. Right, so I should say first that this is joint work with some of my colleagues in Oxford, Carol Mack, Luc Ong, and Dominic Wagner. And the entire talk is about this one theorem, which is that the density of an almost surely terminating probabilistic program is differentiable almost everywhere. And so I'll spend time talking about what this is saying, why it's important for probabilistic programming, and why it's true. Okay, so I think most people will know this, but I'll say it anyway. So the standard distributions in probability theory have a density. It's a positive function. It's a positive real function. So this is what it looks like for the standard normal distribution, which I'll use quite a lot in the talk. So standard distributions have a density, but probabilistic programs can also be seen as having densities. This is a very basic example of a program with two variables, x and y. And so because it has two random variables, you can see the density as a function on R2, which you can just get by taking the product of the individual densities of the random variables. Okay, here's a plot of it. So in this example, obviously it's differentiable because it's a product of differentiable functions. But things will get a bit more complicated in probabilistic programming. So this is important because the density is used for inference, right? So most inference algorithms will operate on the density of the program, trying to normalize it often. And in particular, the gradient of the density is useful for certain algorithms. So HMC, which is used in Stan, for example, Maria talked about that, and variational methods as well use the gradients of the density to compute a posterior. So that's why this theorem is useful, because if the gradient of the density doesn't exist with probability 1, you might run into some problem and the algorithm might fail. So you need a theorem like this to tell you that the inference algorithm is correct. Okay, so with these differentiability questions, things get interesting as soon as you have conditional statements, right? If statements. So here's this very simple example. So if you have a random variable, says it's programmed with two random variables, again, x and y. Here you sample x, and then you look at the value of x, and you sample y with a different distribution depending on whether or not x is less than 0. So this is still, two random variables. So the density is also a function on R2. But this time, of course, you have to define it in a case by case, right? If x is less than 0, the function is different to when x is greater than 0. So I've drawn a plot of this, and you can probably see that it's not differentiable. In fact, it's not even continuous at this set of points where x is equal to 0. And so it's potentially problematic. But of course, this is a measure 0 set in R2. And so, in fact, this function is almost everywhere differentiable, and we're okay. So the main point here to remember is that the fundamental thing in studying differentiability is branching, right? So I'll use a lot in the talk these little drawings of programs as trees of samples, so you can see the branching structure of the program. Right now, I annotate the edges with the particular values that x takes on each branch. All right. Things get even more interesting when the dimension of the density varies. So this is when, for example, you have a different number of random variables on each side, on each branch of an if statement. Okay, so it might be something like this, which you can draw as a tree. And you can see on one side there's three random variables and 2 on the other side. So here, talking about the density is a bit more tricky, but you can still do it. It's a function defined on this set, where you can see that the value that x takes determines how many other variables there are. And for reasons similar to the previous example, this is also differentiable almost everywhere. It's not difficult to see. And for proving the theorem, it'll be more convenient to see this density as a partial function defined on R3 union R2, right? So it's a partial function, which means sometimes undefined, but it'll be defined on the set above. And this is easier because then we can talk more generally about programs of this kind, and we don't have to really worry about the particular condition in the if statement. And for programs like this, as long as you don't have any loops or recursion, right, the density of a program without loops or recursion is differentiable almost everywhere. And the kind of key insight is that for such a program, the number of samples is always bounded in the sum k, such that you can see the density as a partial function on this union, right? R1 up to R0 up to RK, I should say. Okay, and then you can see that on each component it's a differentiable function, and you can reason quite easily to show that it's differentiable almost everywhere. So now let's add recursion to the language, because that's when things get more complicated. So when you have recursion in the language, the density of a program, you can still see it as a partial function of the same kind, but now you have to look at this infinite union of Euclidean spaces. And in fact, the density function is defined only when the program terminates, right? So this big infinite union is another name for it is the set of lists of real numbers, right? Finite lists of real numbers, which we call traces often. And so given a trace, you only return a value for the density when the trace gives you, when there is an execution of the program which returns with this trace. So this is not new here. Many people have considered this kind of formalism for talking about the densities of programs, of probabilistic programs. But here we notice that this is problematic for this theorem of almost everywhere differentiability, because in a language with recursion, you can write a program like this one, where you sample an x from a normal distribution, and then you return if it's rational, and otherwise you loop forever. So this isn't a real program, but you can write a program that does that. And the problem is that here the density will only be defined on the subset of rationals, right? It's seen as a subset of the list. And of course, if it's only defined on the rationals, then it's not differentiable anywhere on R. And if it's not differentiable anywhere on R, then it's not almost everywhere differentiable, right? Because R is not a measure zero set. So we want to avoid things like that, because in particular, they're, well, as far as I can tell, not very interesting for probabilistic programming anyway. And so we're going to restrict ourselves to almost surely terminating programs, and show that actually you avoid this example altogether. Avoid this problem. Okay, so I've made the main points that I think you need to take away. So the theorem hopefully is clear now. But I just wanted to say a few more things about this thing that we call symbolic operational semantics, which is what we use to prove the theorem, and to reason about density functions for probabilistic programs in general. And then I'll say a bit more about difficulties you get when you add conditioning in the language, and something we didn't really expect. Okay, so to begin with, I want to talk about the standard, or I should say, one standard way of doing operational semantics for probabilistic programming. So this is the program I had before, in which you have a conditional and then varying dimensions. And the way to describe the semantics of this program is as a sequence of execution steps or reduction steps, right? So we're going to rewrite this program as it executes. But what we're interested in is computing this density function at the same time. And so I'll give you an example of using the semantics to compute the value of the density at this trace, 0.3, 0.5. Okay, so we start by sampling every time. So the idea, the basic idea is straightforward. Is just every time you need to sample, you just take an element of the trace. So the first time we need to sample x, we say x equals 0.3 and replace x with 0.3 everywhere in the program. So then this gives us the if condition 0.3 is less than 0, which is false, of course. So we take the else branch. And this leads us to having to sample y, and we take y equals 0.5 and return. And by doing that, we can see that we accumulate the density function by just taking the product of all the samples that we made through the execution. Okay, so hopefully this is straightforward. It becomes a bit more complicated when you need to define it in general, but it's nothing too difficult. And this is nice, but all this is doing is giving you a procedure for computing the value of the density given a particular trace, right? It's not very good for reasoning more globally about this density function, which is what you need to do in order to talk about differentiability. So instead, we look at this symbolic semantics, which it looks very similar, except we're not going to look at particular values of x and y. We're going to keep this abstract. And of course, we'll have to do this for every component. Here, I'm just doing the R2 version, but we have to do it for every possible trace, or length of traces, I should say. And so this is how it goes. So instead of having a particular value for x, we keep it abstract, and we introduce this parameter, little x, lowercase x, and replace x with little x. But then at this point, the technical step, I should say, so is that we don't have a value for x, so we don't know which branch to look at. So we just look at both and keep track of the conditions that we've had to assume in the execution. Okay, so assume that x is greater than 0, and continue in the else branch, sample y, and return. And so then we have an expression for the density of a trace xy, assuming that x is greater or equal to 0. Okay, but this is already quite good. We can reason about many of the traces, and if we do that for all the branches, for all the possible dimensions, and there's countably many of those, we're done. And you can see, of course, that this is differentiable on each branch. So I didn't really want to go into the details of how you present this symbolic semantics generally. I just want to give a quick idea in case you know about operational semantics and people are interested. So generally, you might say, so this is the format of the rules, the reduction rules that we look at. Generally, you might just say in the standard semantics, you might just say p reduces to p prime, and then maybe you keep track of the value of the density as you execute. But here, our programs have these new variables, right, which are the little x and little y, which we need to keep track of. So these are the x's and x prime in the rule. And then we need to keep track of this of some other information, which is the conditions that these parameters have to satisfy, right? So what we do is we keep a subset of Rn containing the possible values for this particular branch to be a valid execution. Okay, and then the density will then be a function defined on U, and the theorem basically reasons on these execution steps by saying that if PDF is differentiable, then so is PDF prime. Essentially, is the idea. And this is enough. Okay. Now let me move on to this issue with conditioning, which I mentioned before. So we use score to talk about conditioning. So score is also called factor or observe or condition sometimes, and the idea is score just multiplies the current density by a particular value. So here's an example of how you might use score. I mean, I'm sure most people know this, but you sample a value for x, and then you reweight the density based on some observations. So what this is saying really is that you're observing, say, 0.3, which might be your data point or something, from a normal distribution with mean x. This is the idea. And then we'll try and normalize that. But anyway, so score is a primitive that you add to your language to talk about conditioning. And there's an issue when you add score, which is that then you can have kind of pathological examples, which we'll then have to remove. So in this new example, I sample value for x, and then I branch not on the value of x itself, but on the value of f of x, where f might be some function I have in the language as a primitive. And if you're not careful about which primitives you allow in the language, things might break. So I should say on each branch of the if statement, you score with a different value, which will then affect the density, of course. So the density of this program is not differentiable at the boundary. So at the boundary of the condition, which here is the zero set of this function f. And if you're not careful, there are differentiable functions f for which this is a non-measure zero set. So these can be things that you can construct with Cantor set-like things, where you just get a function as a limit of continuous functions, and you can construct pathological examples like that. It's not very natural, and so it's actually quite easy to remove them. And we can show that the theorem holds for analytic functions. So an analytic function is it's a mathematical definition, but it says the Taylor series of the function converges locally to the function itself. But it's basically contains all of the functions that you might care about in probabilistic programming. We show actually that the theorem holds a bit more generally than that. We in the paper we discuss conditions that the set of primitives has to satisfy for the theorem to hold. But essentially, all functions that you might care about are included in this. But you have to say it for the theorem to hold. Okay, and this is all I had to say. So I'll just conclude by saying that this was an open problem originally asked by Hong-Sok Yang, and he asked exactly that: can a probabilistic program have a density which is not almost everywhere differentiable? And so the answer is yes, namely if you have a non-terminating program. But if you ensure it's almost surely terminating, then no. And so Hong-Sok himself with collaborators had looked at this already, but for a much simpler probabilistic language. So we extended that proof to a general higher order language with recursion. And as I said at the beginning, this result is interesting because you can then use it to show correctness of certain gradient-based inference algorithms for general probabilistic programming. And the final thing that I wanted to mention is that this is related to questions that people in differentiable programming have been thinking about. For deterministic programs, which you can, for deep learning and so on, you're in gradient descent, you're interested in knowing when programs of type Rn to R are differentiable. And actually a corollary of our result is that if these programs are almost surely terminating, then they'll also be differentiable almost everywhere. But this is, other people have discussed this and proved this kind of result before, so this isn't exactly new, but we get it as a corollary. Yeah, that's it. Thank you very much.
Thank you, Hugo. That was an excellent talk. So there's a question. There are a bunch of questions from the audience, but one that I'd like to highlight was: is it reasonable to look for a property like, let's say, that if a program terminates with some probability p, that it implies that the mass on the set of points where the PDF is not differentiable has small measure. So basically looking at finite non-termination probabilities, and the relationship about what you can prove, relaxations of your result. And one example might again be like a probabilistic context-free grammar that places finite probability mass on infinite length derivations.
Yeah. So yeah, sorry, I'm looking at the question at the same time, trying to pause this. So I'm not sure. I think it's certainly possible to extend this to yeah. So what we have is quite a strong requirement that you need to have almost sure termination. And it's possible that you can do that. Yeah, I mean, I can see if you look at the branches in the program, you might be able to show something like that. I don't have an immediate answer, but yeah, it seems reasonable.
That's interesting.
Um,
And one other question from the audience is, are the conditions you give on primitives necessary and sufficient? And there's a connection being asked about to recent work on piecewise analytic under analytic condition functions.
Yes, so I think so. Yeah, I mean, some of what we've done, some of what we talk about in the papers is kind of inspired by that work. And so you can take those as primitives, I think. They are, I mean, they are necessary and sufficient, but they're yeah, I should say, yeah, the answer is yes. And this is an example that fits the requirements, I'm pretty sure.
Great, thank you so much. So I'd like to introduce our next speaker.